Welcome to the Deep Dive. Today we're tackling something really quite groundbreaking, actually. A new way AI is, well, cracking the code of formal mathematics. We've got the technical report here on the Kimina-Prover Preview model.
Right.
And honestly, even if proving theorems isn't your usual thing, the implications here are, well, they're fascinating for anyone keeping track of big leaps in complex areas.
Absolutely. And our mission today really is to kind of cut through the jargon. We want to understand what Kimina-Prover is doing, how it works, what makes it different from, what came before.
And why these results are such a big deal, right? Especially if you're trying to quickly grasp these big advancements.
Exactly. Staying informed is key.
Okay, so let's dive right in. What makes Kimina-Prover different? The researchers talk about this. Reasoning-driven exploration paradigm.
Right. That's the core idea.
What does that mean exactly in practice?
Well, the key thing is it doesn't just search like brute force. It internally reasons through the math problem, kind of like a human might think through it. So instead of just, trying millions of possibilities, it's developing a logical argument step by step, but using the formal language lean for.
Lean for. Heard of that. It's for checking proofs rigorously.
Exactly. So the model is generating and refining these formal steps based on its own internal, thinking.
So it's not just finding the answer, it's building the path, the logical path.
Precisely.
And to show how well this works, the report, it kind of throws out a pretty impressive number right at the start, doesn't it?
It does, yeah. On the mini F2F benchmark, that's a set of really tough, Olympiad-level math problems put into Lean 4.
All right, I remember that benchmark.
Kimina-Prover hit a new high score, 80.7% accuracy. Now, that's using a specific measure, pass at 8192.
Pass at 8192, meaning it gets, 8 out of 192 tries?
Basically, yeah. It reflects the probability of finding a proof within that many attempts. And the previous best system, something called BFS Prover, that was at 72.95%.
Wow. So 72.95 up to 80.7. That's almost an 8-point jump.
It is, and that's significant progress. Gains are usually hard-won in this area. It really suggests something fundamental has changed in capability. They have a figure 1 that shows this pretty clearly.
An 8-point jump. Yeah, definitely something to notice. Now, here's something that caught my eye. The report says Kimina-Prover's performance gets better, consistently better, as the model gets bigger. Why is that such a big deal?
Yeah, this is crucial. And it's where Kimina-Prover really sort of stands out.
Okay.
Because unlike what we've typically seen with neural layer improvers before, they saw this clear, steady improvement. Performance climbed as they scaled the model from 1.5 billion parameters to 7 billion, up to a huge 72 billion parameter model.
But don't bigger models usually do better in AI anyway? What's different here?
Well, yes, generally. But that consistent scaling, that trend, just hadn't really been observed reliably in formal mathematics before this.
Oh, okay. In this specific domain.
Exactly. So it suggests that with this reasoning-driven approach they're using, the larger models aren't just memorizing more stuff. They seem to be actually getting better at the core task of mathematical reasoning within this very strict logical system.
So bigger really means better reasoning here, not just more data recall.
That's the implication, yeah. A fundamental improvement in handling complex arguments as the model capacity grows. It's pretty exciting.
Okay, so it's reasoning internally. Bigger is better for that reasoning.
Okay.
How does it actually do the thinking? How does it manage to produce these formal proofs that Lean 4 can actually check and say, yep, that's correct?
Right. This is where their concept of the formal reasoning pattern comes in. It's quite clever, actually.
Okay.
During the training phase, they basically encourage the model to show its work, to make its internal thought process explicit.
How?
It uses these special tokens, think and think. Between these, it puts its reasoning, and it mixes things up in their informal thoughts, like in natural language, alongside actual snippets of Lean 4 code.
So like notes to itself, but mixed with the actual code it needs.
Kind of, yeah. And those Lean 4 snippets are also marked with special tokens. But here's the kicker. Most of the code it generates inside these think blocks has to actually appear in the final verified proof.
Oh, interesting. So it can't just ramble on. The thinking has to be relevant to the final output.
Exactly. It forces an alignment between the informal plan and the formal execution.
So it's like showing its work in a way that humans can sort of follow, and in the precise language that Lean 4 needs.
Precisely. They have a diagram, figure 2, that shows this pattern. And this showing the work part is a bit of a game changer.
How so?
Because we can actually see how the AI is approaching the proof. It's less of a black box compared to older systems just spitting out commands. It helps the model learn that bridge between, a mathematician's intuition and the strict rules of the formal proof.
That makes a lot of sense. You can follow the train of thought. Okay, so did it learn this? How do you train an AI to do this formal reasoning pattern?
It's a multi-stage process. First, they use something called auto-formalization.
Auto-formalization?
Yeah, it's basically automatically translating math problems written in normal language, like English, into the formal language of Lean 4. This creates a big starting data set.
Okay, gets the problems into the right format. Then what?
Then comes supervised fine-tuning, SFT. This is where they show the model examples of this formal reasoning pattern, the thinking mixed with the code.
Using what kind of problems?
Interestingly, they used challenging problems, like Olympiad-style ones, that were actually synthesized by another AI Claude 3.7 Sonnet.
Wow, AI generating training data for another AI.
Yeah. So this SFT phase gives the model a solid foundation, showing it how to structure its reasoning and code together.
Okay, so it learns by example first, sees how to lay out the thinking in the code. What's next after that initial learning?
After SFT, they shift to reinforcement learning, RL. This is where the model tries to solve problems itself.
It gets feedback.
Exactly. It gets a really simple reward. 1, if it spits out a completely correct proof that Lean 4 verifies, and 0 otherwise. Pass or fail.
Binary reward. Okay.
They use their own RLL pipeline for this, the Kimina-Prover 1.5 pipeline. The report mentions the specific math behind the learning the loss function in equation 1.
Right. Now, I imagine generating perfect formal proofs all the time is hard. Do they run into issues keeping the model, following the format during RL?
They did. They mentioned this problem called format collapse.
Format collapse.
Yeah, where the model might just stop generating the think blocks or the lean code blocks correctly. It kind of loses the structure.
How? So how do they fix that?
They put in some checks, like making sure each attempt included at least one proper tactic block that's a specific Lean 4 command structure.
Okay.
And ensuring these blocks contained a good chunk of the final code. They also had ways to discard attempts that were clearly going wrong, the ones giving negative learning signals, to kind of nudge it toward better reasoning habits.
Sounds like a very carefully tuned process.
Yeah.
You mentioned Lean 4 verification and something called the Numina Lean server. What role does that play?
Ah, yes, Numina. That's basically the engine that checks the proofs. It's built on something called Lean or EPL, but it's heavily optimized.
Optimize how?
Its main job is to take a proof generated by Kimina-Prover and very, very quickly tell you if it's valid according to Lean 4's rules. They use things like caching results and running checks in parallel.
And the result is?
Up to a 10 times speed up in verification compared to older methods.
10 times faster. Wow. That must make a huge difference for the training loop, right?
Oh, absolutely. Think about that RL phase. The model is generating tons of proof attempts. Being able to check them super fast is crucial for learning efficiently. The report says they could hit 100 verification attempts per second on their hardware setup.
100 per second. That's incredible. Definitely speeds up the whole cycle.
It's a massive infrastructure improvement that enables this kind of RL approach, really.
Okay, so we have this AI, reasons internally, scales well, shows its work, super fast checking. How does it stack up against the big general purpose language models, like the OpenAIs and Geminis of the world? They can do some pretty impressive reasoning too, right?
That's a really good question, and they tackle it directly. Table 2 in the report compares Kimina-Prover to models like OpenAI's O3 and Google's Gemini 2.5 Pro.
On the same benchmark, Mini F2F.
Yep, on Mini F2F, and also on specific subsets like just the IMO problems or just the AI problems, and the results. Well, they're pretty revealing.
Okay, lay it on me. Could the general models hold their own in formal math?
Well, here's the interesting thing. Those big general models, they're actually quite good at solving these problems informally. They can explain the steps in English, maybe like a smart student would.
Right, they can reason about it.
Well, when you ask them to produce a formal, computer-verifiable proof in Lean 4, that's where they struggle. A lot.
Struggle how? Like syntax errors?
Yeah.
Or logical gaps?
Both, really. They often hallucinate steps, make logical errors, or just generate stuff that looks like a proof, but Lean 4 rejects it. It doesn't check out.
Ah, and Kimina-Prover.
Kimina-Prover significantly outperform them across the board in generating correct, checkable proofs.
Any specific numbers?
Yeah, for example, on one measure for the full Mini F2F set, Kimina-Prover got nearly 69% accuracy. Gemini was around 38%, and O3 was only about 25%.
Wow, that's a huge difference.
It is, and the gap was even wider on the harder IMO and AMY subsets. It really underscores that general reasoning ability isn't the same as being able to do rigorous, formal mathematical proof within a system like Lean.
So that specialized training, learning within the formal system, gives Kimina-Prover a massive edge for this specific task.
Exactly, and this actually leads to another really interesting idea they discuss.
Which is?
The potential for Kimina-Prover to actually help bridge the gap between that informal, intuitive math thinking and the super strict world of formal proofs.
Bridge the gap. How would that work? You'd think excelling at the formal stuff is almost separate from intuition.
Well, think about what we just said. The general LLMs can often solve, say, AM problems informally, but they bomb when trying to formalize them in Lean.
Right.
Kimina-Prover's success in the formal domain suggests maybe learning to reason within that strict formal system actually forces a deeper, more structural understanding of the math itself.
So the rigor could actually sharpen the intuition, potentially.
That's the fascinating possibility, that the discipline of formal verification might actually feed back and improve even informal problem-solving abilities down the line. It kind of blurs the lines.
That is an interesting angle. Thinking more mathematically overall, maybe. Okay, the report also talks about test time scaling in formal reasoning. What's that about?
Right, that's figure 4. It shows a trend. As Kimina-Prover trains longer and learns to generate longer proofs, they measure this by the number of tokens in the output.
Okay, longer proofs.
Its accuracy on the mini F2F benchmark generally goes up too, which makes sense, right? More complex problems often need longer proofs.
Sure. But is there anything surprising about that?
The pattern is interesting. Unlike in informal math, where accuracy might climb pretty smoothly, the accuracy graph for formal reasoning here is much more jumpy, volatile, ups and downs, occasional dips, even as the general trend is upwards.
Huh. Why would it be more volatile?
Their thinking is it's probably because structured formal reasoning is just inherently complex, and also the amount of formal proof data they have to train on is still relatively small compared to, say, the entire internet used for general LLMs.
So limited data plus complex task equals a bumpier learning curve.
Seems likely, but the key point is the overall trend is upward. It shows that even with less pre-training data in this specific domain, the reasoning-based approach can scale to handle harder problems that require longer, more detailed arguments.
Okay, so it suggests this approach might work even in areas without massive data sets. Now, one of the claims that really jumped out at me was this idea of a human-like proof style. That sounds almost paradoxical for an AI.
It does sound a bit strange at first, but it makes sense given how it's trained. Remember that formal reasoning pattern with the think blocks?
Yeah, showing its work.
Because it's encouraged to do that, it seems to develop abilities that look quite similar to human strategies. Like it can explore different approaches internally, reflect on its thinking in those blocks. Sometimes it even analyzes simpler cases first to get a handle on the problem.
Really, like trying N1, N2.
That kind of thing, yeah. And the proofs it generates tend to be more broken down, more decomposed into logical steps. They even notice it uses have statements frequently.
Have statements.
Yeah, in formal proofs, humans often write things like have P to introduce an intermediate conclusion P, which they then use to prove the next step. It makes the proof easier to follow.
And Kimina-Prover does that automatically.
Apparently so. It suggests it's not just finding a sequence of tactics, but actually planning the structure of the argument more like a person would. You can see examples of its thinking in Appendix F and proof-style comparisons in Appendix E of the report.
That's actually really cool. It makes the AI output potentially much more understandable, maybe even insightful.
Exactly. And they showcase some specific wins to back this up.
Like what?
Well, they mention it's the first publicly available model to prove a specific IMO problem from 1968. It also did well on AIM problems, handling tricky trigonometry and long calculations using Lean First Calc tactic, which is specifically for step-by-step calculations. Appendix D gives more detail on these examples.
Can you walk through one example, maybe, just briefly, to see that reasoning pattern in action?
Sure. Appendix D.3 has one for an arithmetic sequence problem. You see the model in the think block first laying out its plan in natural language. Okay, I need the formula for the nth term, A1 plus N1D. I'm given the third term and the seventh term. I can set up two equations to find the first term A1 and the common difference D. Once I have those, I can find the 21st term.
Right, standard approach.
Then, right alongside that plain English reasoning, it generates the lean-for code snippets to define the variables, set up the equations HU, A3 equals 10, HU7 equals 22, solve for D, solve for AU, and finally calculate a 21.
Ah, I see. The thought process mirrored directly in the formal code steps.
Exactly. And then it compiles all those code snippets into the final, complete, verifiable lean proof. It's a really neat illustration of that alignment.
That does make it very clear how it works. And how does this style compare visually to, say, that BFS prover you mentioned earlier?
Appendix E has a great comparison using an IMO problem from 1962. Kimina-Prover's proof is noticeably more readable. It's broken down, uses those have statements to structure the logic.
And BFS prover.
Its proof is much denser, more reliant on sequences of tactics without as much explicit structure or explanation. It works, but it's harder for a human to look at it and immediately grasp the flow of the argument. It highlights Kimina-Prover's ability to kind of plan the proof sketch.
Fascinating. A move towards more interpretable AI proofs.
Yeah.
But it can't be perfect, right? Surely there are things it still struggles with.
Yeah.
Did they mention any limitations or failure modes?
Oh, absolutely. They provide a good example of a failure mode they call incomplete case analysis.
Okay, what happened there?
It was an AIM problem from 1987. The model correctly identified some constraints, ruled out some possibilities, but then it basically made a logical jump. It failed to consider all the necessary cases required for a complete proof.
Ah, so it missed a scenario, left a gap in the logic.
Exactly. Even after doing some correct reasoning, it didn't cover all the bases. So it serves as a good reminder, you know. The progress is definitely impressive, but ensuring complete logical rigor across all types of problems is still a major challenge.
Right. It's moving fast, but we're not quite at automated mathematician level just yet. Okay, so to kind of wrap things up for everyone listening, what are the big takeaways from this deep dive into Kimina-Prover Preview?
I think the main points are, first, this really does seem like a significant leap in automated theorem proving. This reasoning-driven approach, especially combined with RL, is powerful.
Right.
Second, the fact that it scales with model size in this domain is a big deal. It suggests larger models can genuinely get better at formal reasoning with this method.
Unlike before.
Unlike what was consistently seen before, yeah. Third, it significantly outperforms general LLMs on the specific task of formal proof generation, highlighting the value of domain-specific training. And finally, this emergent human-like reasoning pattern is really interesting both for explainability and maybe even for the future of mathematical discovery.
That idea of AI reasoning in a more understandable, maybe even intuitive way, definitely sparks some thoughts.
It does, and here's something to mull over. Think about AI not just solving math problems, but developing more, well, intuitive and explainable ways to get there. Could that change how we learn and understand math? Could it start to blur those lines between formal rigor and human intuition?
That's definitely a provocative thought. Where can people go if they want to dig even deeper into this themselves?
So the researchers have actually open-sourced distilled versions of Kimina-Prover, the 1.5 billion and 7 billion parameter models.
Oh, great.
Yeah, the link to their GitHub is in the abstract of the technical report. So if you look up the paper, you should find the link there to explore the code and the models.
Fantastic. Well, this has been genuinely insightful, a really fascinating look at the cutting edge where AI meets formal math. It feels like Kimina-Prover Preview isn't just another incremental step, but maybe hints at a bigger shift. Thanks for walking us through it.
My pleasure. It's definitely an area to keep a close eye on. The future here looks pretty exciting.